This is Unit 1, Lesson 5, Patterns and Relations in Tables. And hopefully by the end of this lesson, you'll be able to create a table of values from any linear relation. Now, you don't have to worry about the word linear. We're going to talk about that in Lesson 6. What I'm going to give you a relation, and you'll be able to do an input-output chart or a table of values. You'll also evaluate expressions given the value of the variable. We're going to do that. We're going to evaluate expressions to create our input-output chart or our table of values. So we're going to review a little bit of what we did in Lesson 3. So we started the class. I had the class write an algebraic expression, and it didn't matter which algebraic expression. I'm just going to start nice and easy, and I'm just going to say my algebraic expression is 2x. So 2 times some number. Remember, 2 is your numerical coefficient and x is your variable. And x is a variable that represents any number. What I'm saying now is that I'm going to say that that number is 1. So when I put 1 into this machine, it says 2 times the number. So this is actually saying 2 times 1. It's going to spit out 2 because 2 times 1 is 2. If I put 2 into my machine, it's going to be 2 times that number. So 2 times 2, it should spit out 4. And then I'm pretty sure we can take a look at just the pattern here. So 3 times 2 is 6. 4 times 2 is 8. 5 times 2 is 10. 6 times 2 is 12. So these two, the input and the output, are related by the algebraic expression 2x. Okay, well, let's go on and answer a few more questions. How is the output related to the input? Well, there you go. The output is related to the input by multiplying the input by 2. How did you decide which algebraic expression to use? So this was just because I allowed the class to pick their own algebraic expression. So I just was curious as to why they picked that one. So some students wrote, oh, because it was used in a class, or I remember that it was a little bit easier. It's just an open-ended question. And here it says, what do we call the number that does not have the variable? So it's just a review. It's called the constant term. And I'll give you an example here. In our algebraic expression here, we don't have a constant term. Actually, it'd be 0, but we don't have one. Here, if I have 2, if my algebraic expression was 2x plus 1 is my constant term. It's the one that does not have the variable. What pattern do you notice in the output numbers? Okay, well, let's take a look at the output numbers. Remember, patterns can go this way, and we do that. We use that pattern by doing our algebraic expression, but we can also find a pattern just by looking at our outputs. Here we have plus 2, plus 2, plus 2, plus 2. So my outputs are going up by 2. Increasing. Let's use the good word. Increasing by 2. How's that? We're going to use this later on in our, this is going to be really, really important later on. I think a little bit later on in Lesson 5. So just hold on to that thought, the output patterns. So an input-output machine represents a relation. So here the relation is 2n plus 1. Another way that we can show the relation, we can do it by an algebraic expression or a relation, or we can do it in an input-output chart. The number called the input is what we actually substitute in. So that's what we substitute in. And then once we do the order of operations, multiplication before addition, it will spit out a number, and that's called our output. So let's use the algebraic expression 2n plus 1 to answer the questions below. How can you find the output when the input is 5? Okay, well, I'm saying this algebraic expression says 2 times some number plus 1. And now I'm telling you that that number is 5. So remember, I start with the expression, I substitute my variable in. Remember, this is 2 times some number, so 2 times, and I'm saying that number is 5, and then I do the order of operations. Multiplication comes before addition, so 10 plus 1, and that will give you 11. Now, what happens if your your input now changes to 8? Well, the relation doesn't change. It's still 2n plus 1, but my input changes. Now, remember in class, I said we don't really want to use the multiplication sign because sometimes it can confuse it with the variable x. So instead of putting a multiplication sign, we can put brackets and we assume that there's a multiplication sign there. So 2 times 8, remember it's not a digit, there's an operation there. It's 2 times 8, which is 16. And 16 plus 1 is equal to 17. So what happens if we just change the order? Well, if I have 2n plus 1 and 1 plus 2n, the answer or the output will not change. Whoa, my apologies. It will not change. And the word I'm looking for is I can't believe this is going to be going on the internet. Commutative. I can never pronounce that word. My apologies already. It's commutative. So it doesn't matter if I have 2 plus 3, it will always equal to 3 plus 2 because the order in addition doesn't matter. It's commutative. It will always give you the same answer. So if I go 2n plus 1 and 1 plus 2n, I will always get the same result. So what we're going to do is we're going to do the input-output machine now for this relation. So we're going to create a table to, I'm just going to move this over here, to create this table, or that will give me a table that shows the relation 2n plus 1. So I already calculated a couple here. When n is equal to 5, we said the output was 11. So let's put that in here. Why do more work, right? So I want to find out what my output is when my input is 1 and my the relationship between the input and output is 2 times this number plus 1. So let's start with our expression. Let's substitute our number in. Remember, we don't want to put the multiplication sign anymore. If you have to, just to remember, go ahead. It's okay. But this right here, when I put brackets around that 1, this tells me that I'm multiplying. And 2 plus 1 is 3. I always do multiplication before addition. So when I input 1 into my machine, it spits out 3. So now let's do the same thing for 2. Let's start with our expression. Sorry, I have a little bit of a cold here. I substitute my number because this says 2 times some number. I'm saying now my number is 2. And then remember, this is multiplication here. That's why we have brackets. We don't change it to 22. It's 2 times some number. So 2 times some number is 4. 4 plus 1 is 5. Let's do one more. 2 times 3 plus 1, because I'm now saying my number is 3. 6 plus 1 is equal to 7. So now, instead of having to do all of this work, we can start looking at our output pattern. Plus 2, plus 2. Let's try plus 2. Plus 2, that works. And look, and we got to our 11, plus 2. So I'm pretty safe to say that you know that this should be 13. If you want to check, we can always substitute 6 in. 2 times 6 plus 1. 2 times 6 is 12. 12 plus 1, 13. We got it. It matches. So we don't have to do all this work once we know what the pattern is. So find the pattern and then continue on just with your output pattern. So if I want to describe the relationship between the input and output, I must multiply the input by 2 and then add 1 to get the output. That's how you would describe it in words. I have to multiply the input by 2, add 1, and then it will spit out the output. So what we're going to do is we're just going to quick check here. Some of you guys will probably be able to do this in your head. If you can't, then you can do it on a scrap sheet of paper and then insert your numbers onto your chart. So I'm saying that my relation is n plus 5. So some number plus 5. And now I'm saying that my number is 100. So I should have 105. This should be 106. 101 plus 5. 102 plus 5. 103 plus 5. So my pattern is add 5 to my input to get the output. Okay. This one's a little bit tougher. So this is saying 3 times some number plus 1. So 3 times some number. I'm saying now my number is 10 plus 1. I do my order of operations. So this is 30 plus 1. Multiplication comes before addition in the order. So this is 31. So let's see what if I input 11. I'm going to go up here. So 3 times 11 is 33. Plus 1 is 34. So now we can kind of take a look because the pattern should stay the same. This is plus 3. So now we can just use the pattern of plus 3 and plus 3 in order to fill in the chart. Okay. Here, sorry. Let's go back and do our pattern. So multiply the input by 3 and add 1 to get output. Sounds good? Okay, let's take a look at the last one. Again, this is really tough because you're doing 2 operations. So I'm going to go down here. So 5 times 1 minus 2, because this is 5 times some number minus 2. So 5 times some number, sorry, now I'm saying that number is 1. So 5 times 1 minus 2 is 3. Now I've also seen this. It's up to you. If you write small, you can go 5 times 2 minus 2 right here. And if you can do this mental math in your head, go ahead. I know some of you can do it. 5 times 2 is 10. 10 minus 2 is 8. If you can't do that mental math, then you need to come down here and 5 times 3, input your number, minus 2, do your order of operations, 15 minus 2 gives you 13. Now take a look. I'm adding 5, so I have to add 5. That should be my next one. Let's take a look at my pattern. Multiply the input by 5 now. and add, oh, not add, subtract this time. 2 to get output. Okay, well, let's just see if we see a little pattern. Just keep this in mind. Here, when you don't have a number in front of your variable, you assume it to be 1. We talked about that in lesson 3 a little bit. So let's just put an invisible 1 there. What am I adding here? I'm adding 1. Here, I'm adding 3. Look at my numerical coefficient. Here, I was adding 5. Look at my numerical coefficient. Okay, so there's a pattern with your output and your numerical coefficient. So what we did in class was what I gave out some cards and we tried to see what that relationship was. And that's why I just brought that to your attention in the last example, because we can't really do this, you know, like it's a collaboration thing. So that's why I kind of brought it to your attention. But let's see if it works in the next examples. Okay, so let's look at our output. We're going up by 1s here. Okay, but let's look at the rule. How do I get from 1 to 2 and 2 to 3 and 3 to 4 and 4 to 5 and 5 to 6? Well, I take whatever my input is and I have to add 1. Well, what's my numerical coefficient? 1. So it does work. Let's take a look here. +1, +1, +1, +1. Okay, let's look at our rule. How do I get from 15 to 11? Well, I have to subtract 4. Let's see if it works for all of them. -4, -4, -4. So whatever my input is, I have to subtract 4 and I'll get my output. What's my numerical coefficient? 1. Works. So your output pattern is always your numerical coefficient. Let's see if it works here. We add 3, add 3, add 3. Just out of curiosity, what do you think the numerical coefficient is? Should be 3n, right? Okay, well, let's see. 4 times 3 is 12. 5 times 3 is 15. 6 times 3 is 18. Look at that. So whatever my input is, I have to multiply it by 3 and I'm going to get my output. So my rule is 3 times n. And again, we never put our multiplication sign anymore because this means something different in grade 9. This is 3xn. So we never ever put the multiplication sign anymore. Okay, so don't do that. Just write it as 3n. I will know and everyone will know in the math community that it's 3 times some number. Okay, so let's write a relation here. If I go 1 to 2, I can get from 1 to 2 either by adding 1 or by multiplying by 2. Well, let's see if that same rule applies for all of these. Well, if I go 2 plus 1, I'm not going to get 5. And if I go 2 times 2, I'm not going to get 5. Well, that kind of that's not good. So let's go and erase these and let's use what we learned about our output pattern to help us. So what are we adding here? Well, we're continuously adding 3. So what's my numerical coefficient? It has to be 3n. That 3 that's that relationship that we've been working this whole lesson on, is that this output pattern, whatever you're adding here, whatever your output is increasing by, that is your numerical coefficient. But just wait, we're not done yet. Okay, so now we have to say 3 times our input. So 3 times our input doesn't give me 2, it gives me 3. So what do I have to add or subtract to get to 2? Well, I have to subtract 1. Let's see if it works with the other one. 3n just says 3 times a number. So let's go 3 times 2. So 3 times 2 is 6. 6 minus 1 is 5. Perfect. Okay, well, let's try one more just to make sure if that's our rule. 3 times 3 is 9, minus 1 is 8. So my relation is actually 3 times the number, subtract 1, and it will always give me my output, no matter what that number is. There's my relation. Now, if you want to write it as n arrowed 3n minus 1, that's fine because a relation is comparing two different things. But you will see all I'm looking for is this, just that algebraic expression. Okay, this one's a little bit tougher, but let's go on to the next one and we'll come back to that one. I did that in class and I might change the order next year. So which rule applies to the input numbers in order to get the output numbers? Well, do I have to add 3, subtract 3, multiply by 2, or divide by 2? So if I add 3 to each of these, and remember that rule has to work for all of the numbers, I actually get my outputs. So my answer in this case is A. So this is a similar type. This is a test question. It would be an easier test question, but it would be a similar test question. I'll give you a chart and you have to figure out what rule connects the input, what relation connects the input and the output. So in this one's very similar to one again. This is a test question. Very similar. I'm going to take the number 8 and drop it into the machine and it comes out as 2. So the table below shows some other input-output data for the machine. So notice I go 8 to 2 and 10 to 4 and 15 to 9. Well, these inputs are not in order. So why don't we just change it? Why don't we put 10, 12 to whatever and go 15 to 9? And let's put our inputs in numerical order. Let's put them in order from lowest to highest. Now, I don't think we even need this number because we can figure out the pattern here. Inputs 8, 10, 12. Output is 2, 4. Well, it's going up by 2s, so it must be 6. Whoops, 6. So sometimes information is put into a question that is meant to distract you, and that's called extraneous information. So don't be distracted. Don't get tricked. Okay? You just really only needed the first 3 pieces of data. Okay, let's go back to this tough one here. My outputs are going 2, 3, 5, 8. So if I go, and these ones are going up by 2s. So this one should be 4. 4, 6, 8, 10. This one should be 12. And then this one jumps 2. So yeah, that makes sense for the 16. Okay, so notice how these ones are going up by 1s here. And let's forget about this. That's our extraneous information. We don't really need that to answer the question. So these ones are going up by 1s and these ones are going up by 2. So we completed the table, but now this is the hard thing. It says find the rule. How do I connect the 4 to the 2 and the 6 to the 3 and the 8 to the 4 and the 10 to the 5 and the 12 to the 6? Well, if you can see it right off the top of your head, all I did was I divided all my inputs by 2 and I get my output. So those ones are a little bit tougher when you actually have to divide. So here's one way you can write it. And here's like the grade 6 way. If you actually use the division sign, that's fine. I'm not going to mark you wrong in grade 7. In grade 8, the division sign is gone, and you actually write it as in a fraction form because this line means to divide. So now we have page 27, number 1, 2, 4, and number 7. And if you have any questions, come see me in class.